So let's start. My name is Sillin Fu, and welcome to my PhD defense. And my supervisor is Dr. Augustin Hua. My thesis title is Tailoring Photosecond Laser Filamentation in the Atmosphere. So before we get into my result, I would like to introduce you what is filamentation. So in principle, filamentation means your laser peak power over the critical power. And in air with 800 nanometer laser, and it's 5 gigawatt. And if you have a photosecond laser, it's a millijoule level. And when this kind of laser propagated in air, there's a dynamic computation between the focus and defocusing happen. And the Kerr effect will lead the surfocusing, and the plasma will diffract your beam. And by this dynamic computation, we can generate a stream of plasma. So in principle, filamentation is a stream of plasma. And inside of this plasma, the clamped intensity is over 10 terawatt per centimeter square. Filamentation is very useful. So I will introduce you this part by the different time domain. So in the photosecond time domain, the laser come and interact with the gas molecule and generate the filamentation. So people focus on the supercontinuous generation and the white light conical emission. Since the filamentation can deliver very high intensity laser over a long distance, so people also use this method to do leads. And after the plasma generated, people focus on the secondary radiations, like terahertz pulse or air lasing. And this plasma can also be used to get a microwave. And after the plasma lifetime, people focus on the hydrodynamic effect and the low density gas channels. So here I show an example of this hydrodynamic. So the laser comes from your right side and generate the filamentation in this position and leave a low density channel. And on the both sides, there is a high density channel. This hydrodynamic, people use it to clean the cloud or fog for the optical communication, and also to gather discharge. Like 2 years ago, our group demonstrated this hydrodynamic can be get lining. And also, this hydrodynamic can be used to achieve optical air waveguide. In my thesis, I mainly focus on the organization of the filamentation, and this work is for, there are 3 parts of my work. So on the first part, it's a transverse plan, and it's mainly to optimize the air waveguide. And the second part, it's on the laser axis. It's try to get a longer discharge. And the third part is spatial temporary control of the filamentation. It's to optimize the terahertz emission. I also put my paper in here. If you're interested in some part, you can just look at my paper and to get more detail. So let's go to the first part, air waveguide. So how to create an air waveguide? Usually, if you want to generate an air waveguide, you need your beam with a hollow structure. Since your beam with a hollow structure, so you can generate some filamentation with a hollow structure. And after the plasma lifetime, each filament can generate a shock wave in all directions. And maybe after like a few hundred microseconds, these shock waves will gradually evolve into a larger hollow structure. And if you look at this hollow structure, you will find in the center, we generate a high density channel. And around the center, we have a low density channel. It's corresponding to the fiber clamping and fiber core. So 10 years ago, American group first demonstrated this air waveguide over 70 centimeter by 4 filaments. So we can see here very clear 4 filaments. And if you want to generate a longer air waveguide, so of course you need more filament. But how can we get it? So of course we can add more phase lobes. Like in here, he used 4 lobes. We can add 8 lobes, and to get 6 or 8 filamentation. But it's not very simple and very beautiful. So is this a way to naturally generate a multi-filamentation with a ring shape? Yes, of course, we can use vortex beam. So before I introduce you what is the vortex beam, I would like to introduce you what is a super Gaussian beam, since it's our laser output. So for the super Gaussian beam, it's in the phase domain, it's very flat phase, and in the intensity domain. So here is the result. We use a photosynthetic paper to measure this super Gaussian beam. So we can see in the intensity domain, it's also very flat. And for the vertex, it's just the way add this vertex phase to the Gaussian beam or the super Gaussian beam. And this phase variation from 0 to 2 pi, and then we can get a beam with a ring shape. And maybe you notice there are some small structure in here. It's just because we use a state special phase mask, so they can generate some diffraction structure. So here's our result. So here we use a CCD camera and at very, very low laser energy and place this camera at the focus position. So we can see even in the focus position, the vertex beam keep a hollow structure very well. And after that, we increase the energy to get the filamentation. So here it's a result. We use photosynthetic paper to measure the beam and the plasma distribution along the z-axis. So we can see at least over 1.5 meter, the filamentation keep a quite good hollow structure. Like I just mentioned before, this air waveguide is achieved by the low density channel, not plasma itself. So we build this setup to check this low density channel. So our beam is come from here and focused by a lens and generate some filamentation. And another side, we use a nanosecond probe laser and synchronize with the pump, and we can adjust the delay so we can start this low density channel after the filamentation at a different time. Then we use a waveform sensor to detect this probe. So here's the result. So we can see after plasma generated 1 microsecond, we observe 5 to 6 channels. And after 500 microseconds, these 5 to 6 channels gradually evolve to 2-man channels. And we can also do an Abel inversion to get a real air density variation like that. So we can see for the vertex beam, we observe some abnormal structure, like in the center, we have some high density channel, and on the both sides we have a low density channel. So this corresponding to the fiber clamping and fiber coil. So after we get something like a fiber, of course, we want to get something inside. So we build this setup to test if we can achieve air waveguide. So our laser with 25 millijoule and 800 photosecond pulse duration, also 800 nanometer wavelengths, and focused by a 4-meter lens and pass through the vertex faceplate. And in here we use the topological number m equal 4. On another side, we inject a nanosecond laser at 532 nanometer and focused by a 3-meter lens and focus into this air waveguide structure and use a camera to detect this probe beam profile. So here's the result. So figure 8 is no guide effect. So with this case, it means there's no filamentation, there's no low density channel. And we can see after the plasma generated 2 microseconds, we observe this probe beam profile is just to be perturbed by the low density channels. And after 500 microseconds, we observe this hot spot in the center. We consider this part is our guided part. And this waveguide effects lasts up to 2 milliseconds. So in this work, we use the filamentation produced by a vortex beam and demonstrate this vortex filamentation can be used as a guide for a nanosecond laser pulse at 532 nanometer. After we achieve this 2 millisecond lifetime and 1.5 meter long air waveguide structure, we want to do more. So we know when we increase the laser repetition rate, there's a cumulative effect for the low density channel when your laser repetition rate over 100 hertz. So it's raises a question for us if we can generate a permanent air waveguide. So the permanent air waveguide is mean if you keep shooting your laser, this fiber structure will always exist. So we move our air waveguide experiment to this very powerful laser. So the Trump laser, it can deliver 1 kilohertz repetition rate and 240 millijoule and 1 micro center wavelengths and 800 photosecond pulse duration. So I would like to invite you to check this low density channel generated by the different repetition rate laser. So you will find for the kilohertz filamentation, the low density channel are 10 times larger compared to the 10 Hz laser. So if you want to focus this beam to generate this air waveguide, so it's very hard to get a very good hollow structure around the focus. So we have to try unfocus the beam. So we build this setup. We use a trump laser and pass through the 6Q plate I will introduce later. And another side, we use a CW laser, a continuous laser, and use a lens to focus this beam and send to the air waveguide structure. And also use a camera to measure this per beam profile. Here it's the real picture of our setup. So laser is here, and after 60-meter propagation, and we use a mirror to remove the point, and use a camera to detect the probe. So the 6Q, if you look at the phase domain, the 6Q is, there are two phase components. One is 0 and one is pi. And if you look at the intensity, for the 6Q, you will find the beam separated to the 6 parts. So here it's we use a photosynthetic paper to measure the plasma and the filamentation distribution at the different z-axes. So the green part is the filamentation. So maybe now it's not very straightforward, but if I use a ring to fit it, you will find actually we achieved a quite stable hollow filamentation structure over 22 meters. So here is our result. The per beam profile, we measured it at a distance of 60 meters after this phase plate. And figure A is at a different point laser energy. So we can see when the point laser energy over the 61 millijoule, we get this air waveguide effect. And the figure B is we measure the per beam profile at a different delay with respect to the filamentation formation. So we can see here in the 1 millisecond time scale, we get a quite stable air waveguide image. Consider we have a kilohertz laser, so it means we get a permanent air waveguide. Also, we cooperate with Professor Aknong Hwahong and try to simulate this per beam propagated in this air waveguide structure generated by the filamentation. So figure A is our experiment result. The black curve is the air waveguide beam profile, and the red curve is the reference from here. And the figure B is our simulation result. So we can see actually it's in a quite good agreement. So in this work, we generate a permanent dechimetric air waveguide from unfocused filamentation. And I think it's also the first application for this unfocused filamentation. So let's go to the second part, try to get a longer discharge. So how does a laser get a discharge? Usually you generate the filamentation by a photosecond pulse and generate the plasma with the picosecond to nanosecond lifetime. And because this plasma can haze the air, so you can generate a low density channel with a nanosecond to millisecond lifetime. Because it's a low density channel, so in this part, it means there are less molecules. And less molecules is mean the free electron mean free pulse is larger. And the breakdown threshold so is lower. So when you place a high voltage electrode close to this low density channel, then you can get a discharge. So in the air waveguide experiment, we found actually for the Laguerre-Gaussian beam, it's included the vortex and 6 sectors can generate a longer filamentation compared to the super Gaussian beam. So we test if this Laguerre-Gaussian beam can extend the guided discharge. So here it's the result. We use the photosynthetic paper, measure the beam and the plasma distribution along the axis. So we can see for the super Gaussian beam, one big filamentation generated. And for the vortex and the 6 sectors, we have a long filament with a ring shape. Also, we collaborate with Professor Aknong Hwahong to solve the low-linear Schrodinger equation. And here it's our simulation result, so we can see it's in a very good agreement. And for the filamentation length, for the super Gaussian beam, we have 1 meter. And for the vortex beam, we have 1.5 meter. And for the 6 sectors beam, we have 2 meters. So we see an increase of the filamentation length. And then we use a microphone to measure the plasma shock wave, the acoustic signal for the different filamentation. So we can see here the black curve is a super Gaussian beam, and the green curve is a vortex beam, and the purple curve is a 6 sectors beam. So it's very easy to see it's the acoustic signal of the vortex and the 6 sectors are longer. And then we build this setup, try to measure the reduced breakdown voltage. So our laser is singing here and focused by a 5 meter length and pass through the faceplate and send the filamentation to these 2 high voltage electrodes. And we measure the breakdown voltage. So we can see the filamentation produced by the 6Q doubles the length of the guided discharge. And the breakdown voltage, the curve, match the acoustic signal very well. And then we move this setup to the Tesla coin to try to get a longer discharge. And our Tesla coin can generate 315 kilowatts. And when there's no laser, so there's no breakdown, so we can see there's some small corona discharge. And when we use a laser, so we can see a very clear guided discharge. So in this result, we can see the vortex and the 6 sectors, they double the length of the guided discharge. So in this work, we demonstrate the Laguerre-Gaussian filamentation can get a discharge over longer distance. In general, the guided discharge length is limited to the length of the dense filamentation. So usually, we use a focused beam to generate this kind of dense filamentation. But this dense filamentation, it's always around the focus, so usually it's quite short. But how can we break this limitation? So 20 years ago, our group proposed one idea is to achieve concatenant filamentation. And also people use this idea and achieved a longer discharge. But for this concatenant filamentation, it's very clear you need a very complicated time and space delay generator, and it's not very simple. Is it a way we can use a single optical element to generate this concatenant filamentation? Yes, in here we use the multifocal DOE. So for the multifocal DOE, it's like a linear lens. The different radiance will be focused at a different distance, and it can generate a multifocal point with equal spacing and uniform energy in the laser axis. So here it's our setup. So we custom a face mask, a multifocal face mask, to generate 3 different focus position, but you can custom different style like 5 or 10 focus position. And our input beam focused by a lens and pass through this face mask and generate the 3 filamentation. And we can adjust this input laser parameter or the external focus to make this 3 filamentation to merge together. So here it's the plasma luminescence result. So when there's no faceplate, we can see we generate a single filamentation. And with the multifocal face mask, we generate 3 filamentation and it's merged together. And then we measure the luminescence and the acoustic signal. So we can see for the multifocal filamentation, there are 3 peaks for all cases. And this 3 peak is corresponding to the 3 different focus positions. Then we measure the deposited energy for this multifocal filamentation. We find actually it's 50% higher than the classical filamentation. And so we see an increase in the filamentation length by the filamentation generated by the multifocal face mask. And the plasma density is not very different compared to the normal filamentation. So then we try to test this filamentation to get the discharge. So here is the plasma luminescence, and when we place high voltage electrodes close to this plasma, it's this. So for the without the multifocal phase mask, we have 40 centimeter gated discharge, and then with the multifocal phase mask, we have 86 centimeter gated discharge. So in this work, we demonstrate a multifocal beam extends the length of the filament and the gated discharge. So let's go to the last part. Special temporary control of the filamentation for the terahertz emission. So I have to say this started, this filamentation generated by the terahertz generated by the filamentation has been well started over 20 years, and especially for the fundamental case, I mean, use a single color filamentation, and everyone know for the single color filamentation, it can generate a forward conical emission for the terahertz, and we call this forward conical emission as transition Chilling curve radiation. So it means each point of the filament can be regarded as a dipole, and this dipole will interference with each other. And when this dipole move as a velocity of the ionization phone, usually it's light speed, we can get this forward conical emission. So for this later terahertz source, there is a very big limitation for the application. We can only generate a forward emission. But if we want to do some remote detection, of course you want to place your detector as a same position you send your laser. So with this case, you need a backward emission. How can we break this limitation? So I would like to invite you to review this principle of this terahertz generated. So you have a pump laser and generate a forward filamentation, and the dipole moves forward, and then you have a forward emission. But how can you get a backward? I think the most simple way is just to change the word. So if you have a backward filamentation, so the dipole moves backward, so of course you can get a backward emission. The problem is, how can we get there? So in here, I introduce the method. It's flying focus technology. So what is a flying focus? So for the flying focus, it means the different wavelengths are focused at the different positions by a diffractive lens. And we can change the chirp of the pulse, so we can control the sign of the velocity of the ionization phone. So for example, in here, they use a 60 millimeter diffractive lens, and at the positive chirp and the pulse duration is 65 picoseconds, they generate a forward flying focus. And with a negative chirp and the pulse duration is 55 picoseconds, they generate a backward flying focus. Yeah, this one is a forward, yeah. So we have to test this flying focus technology can use to control the ionization phone velocity in air, so we build this setup. So we have a compressed beam, and with 100 picosecond pulse duration, 200 millijoule and 800 nanometer center wavelengths, and separated by a beam splitter, and 99% sent to the compressor 1 to generate a chirped pulse. And with this chirped pulse, we have 0 to 200 millijoule energy, and the pulse duration is from 50 photosecond to 9 picosecond, and focused by a diffractive lens with the focused lens 30 centimeter. And another 1%, we make it pass through the compressor 2 to generate the per pulse. So this per pulse with 10 nanojoule energy and 50 photosecond pulse duration, and use the interferometry or a CMOS camera to observe this plasma formation per size. So let's look at the result. Our laser is come from this direction, from your left part to the right. And this one is the result with a positive chirp, 500 photosecond, and with a 10 millijoule laser. So we can see we generate a forward plasma, very clear. And when we change to the negative chirp, something happened. So we have a 10 millijoule, 6 picosecond, and with the negative chirp. So we can see we generate a backward plasma. And then we build this setup to measure the terahertz generated by this plasma. So our detector at 0.1 terahertz, they can only detect this frequency, and we place this detector 50 centimeter away from the filamentation, and then we can rotate this detector to measure the terahertz angular distribution. So here it's a terahertz result. So for the forward filamentation, we get a very beautiful forward conical emission. So the 0 is the laser direction. And for the backward, we also get a very beautiful backward conical emission. In our experiment, we found actually this flying focus technology can not only control the direction of the velocity, they can also control the velocity itself. So we test it. So here it's the result of the ionization font position as a function of the time. So by this, we can calculate the ionization font velocity. It's here. So the different curve, the curve is calculated by the flying focus theory. And the point, it's our measurement for the ionization font velocity. So we can see for the positive chirp, we produce the subluminal and luminal ionization font velocity. And for the negative chirp, we generate some super luminal ionization font velocities. We have a very traditional mode to explain this terahertz generated by this single color filamentation. And it's proposed by the professor Vladimir Tehonshok. And this version, it's only for the ionization font velocity equal to the light speed. So we also call it the transition Cherenkov radiation. So obviously, it's not very good for our new case. So we collaborate with Professor Vladimir Tehonshok again and try to develop some new theoretical mode. So here. So by this equation, we can calculate the terahertz spectrum power per unit angle. And here's the new version. So it considers all the cases. This means your subluminal, luminal, and superluminal. All these cases can be correlated by this equation. So the first part, it will give you the spectrum distribution, and the second part will give you the angular distribution. So let's check. So here is the measurement of the terahertz emission angle and measured at different ionization font velocity. So we generate a forward and backward terahertz radiation at the subluminal, luminal, and the superluminal ionization font velocities. And here it's our simulation result. So calculated by our new mode. So we can see actually it's in a quite good agreement. And because our detector can only detect the terahertz at 0.1 single frequency, so we calculated this terahertz spectrum for the 3 different plasma densities. It's from 10 to 16 and to the 10 to 18. We have a waveform sensor, so we can detect the plasma density at a different pulse duration. So our plasma density is also in this area. So we can see even for the very, very low plasma density, 10 to 16, we still reach to the 6 terahertz. So it's quite broad. And it's also a similar spectrum as the transition Cherenkov radiation. Another interesting result we found in our experiment is when we measure this signal at 0.1 terahertz as a function of the ionization font velocity. We found actually for the superluminal case, we can always get a much higher intensity signal. And this superluminal is corresponding to the pure Cherenkov radiation. So we can see here for the transition, and the transition Cherenkov is reached to around 500. And for the pure Cherenkov, we have 4,000. So this terahertz energy is increased by an order of magnitude. And we also calculate this terahertz energy by our new mode. It's here. So we can see our simulation it's also support this result. So here it's the transition Cherenkov, and here it's the pure Cherenkov radiation. Another interesting result we found is for this transition Cherenkov radiation, the different frequencies have different angular distributions, we have this equation to calculate it. So for the high frequency, they have a bigger divergent angle, and for the low frequency, it's more close to the laser axis. Then we simulate this angular distribution by our new mode. So we can see when we get this Sillin curve radiation, all the frequency are emitted along a very narrow cone. It's just because for the Sillin curve radiation, we have this equation, so there's no relationship to the frequency, lambda. So this source is very good for the spectroscopy applications. So let's conclude my work. So in the first part, we demonstrated that the filamentation generated by the vortex beam can create a air waveguide. And by using this cumulative effect of the low density channels, we achieved tens of meters of this permanent air waveguide. And for this work, we think this long distance air waveguide can work with the cloud and fog cleaning and to benefit this long range optical communication through the clouds and fog. And also we found this hydrodynamic effect produced by the filamentation, especially for this produced by the high repetition laser, could potentially create some optics to manipulate the laser beam. So in here I show an example. We use, in some case, we get some very beautiful quasi-basal beam just by this low density channel. And for the second part, so we have demonstrated this Laguerre-Gaussian beam filamentation can be guided a longer discharge. And also we propose a multifocus phase mask dismasser to extend the guided discharge length. And for this work, we think this masser can be used to optimize laser guided lightning. And for the last part, so we achieved the backward filamentation and the pure Sillin curve 10 Hz emission. And by the simulation, we found actually this texture source is only few tens of or hundreds of the picojoule. So for the next step, we will focus on to increase this texture energy. For example, to use the two color and the high voltage, or increase the pump laser energy. Actually, I got some interesting results last week. So with the we use some high voltage electrofield like here. So we can see with 11.5 kilowatts per centimeter, and the terahertz increased 20 times. And when we increase the laser energy, for example, in here we have 100 millijoule. The laser energy increased 6 times, so the terahertz increased 25 times. So I would like to thank the people, my jury member, and because they have to read my sources, 150 pages. I think it's not a very easy task. And I also need to thank people, my group, Aurélien, and Yusbiana and Hey, and Fatima, Nicolas, Baptiste, Magili, and Juliette, and Leonie. And I also need to thank my 3 collaborators, Professor Aknong Kwahong, and Professor Vladimir Leonshok, and Professor Yi Liu, and especially for the Professor Yi Liu and the Professor Aknong Kwahong, they are my main defense jury. And I also need to thank the entire lab because I got a lot of benefit from our lab, like people from UPX, the Cedric and Jean-Philippe for me a lot of very expensive optics and never asked me to reiterate. Yeah, but yeah, they're all in a good shape. I will reiterate soon. And the secretary, and I think they did a lot of effort to make me feel better because I don't speak French. And everyone, yeah. And of course, thanks for your attention. That's all.